Hi everybody, this is Jim Aikin, and in this month's video I'm going to illustrate a few things to do with analog type waveforms. What we have here is an analog oscillator. We'll worry about the second oscillator and the other stuff later. The four outputs of this oscillator are going over here to this four-way switch, and the output of the switch is going, among other places, to our mixers so that we can hear what we're doing. So when I unmute the first mixer track, you're going to hear a sine wave. Now, as I go down the switch, we can switch from a sine wave to a triangle, a square, a sawtooth, I guess, is next, and then finally a square wave. So you can look at what you'll see on the scope. You'll see the shape of the waveform. And down here we have a spectrum analyzer, which will reveal the overtone structure of the waveform. So let's do that again. First a sine wave. Now a triangle. You can see there are a few weak overtones in the triangle. Here's the sawtooth. Wow. There's more overtones there. And that's the square wave. In the square wave, some of the overtones are missing. If you compare the square wave with the sawtooth, you'll see that the sawtooth has all of them, and the square wave only has half of them, which is why it has a kind of a hollow sound. Now, there are other features on this oscillator. First of all, we have the analog versus digital switch. This is all digital, of course, but if I switch to analog mode, the oscillator will attempt a little harder to mimic what you would get from an actual analog oscillator. So let's go back to the sine wave, and we'll hit that switch and watch what happens. You can see that the analog version of the sine wave is not perfectly a sine wave. It has a little activity in there. And if we were to go, for example, to the sawtooth, now let's go to the square wave. You can see that the waveform is actually bent a little bit here, where in digital it's straight up and down. That makes almost no difference in the sound, but it is a difference that is caused by that switch. The next thing we're going to talk about is, let's see, what do I have in my notes here? Oh yeah, pulse width modulation. One of the nice things that you can do with analog type oscillators is you can modulate the waveform. In a classic oscillator, you can only do this with the square wave. So this is our square wave. And I've got an LFO down here, a low frequency oscillator. Let's turn that down to a lower frequency. And its output is going up here to the pulse width modulation input of the oscillator. And the amount of this that reaches the oscillator is controlled by this knob here. So as I gradually turn up the knob, you're going to hear a change in the sound, which is caused as the LFO sweeps it. So that's a nice way of adding a little animation to the wave. And if we speed up the LFO, interesting things will happen, which might or might not be useful musically. Okay, that's enough of that. The next thing we're going to demonstrate here is synchronization. I'm going to go back to the sine wave here, turn the pulse width down to 0. This second VCO has an output from its sine wave, which is going into the FM, frequency modulation input. This is the oscillator that we're listening to, but this one will affect its frequency. So let's check out what happens when I pull up the FMCV knob. You can see that the waveform is getting a little weird and the harmonics are getting a little weird, and of course the tone can actually be changed if we change the frequency of the other oscillator. So that's what happens with FM. The final thing we're going to look at is synchronization. There's a sync jack here. So I'm going to move this guy over to the sync jack. Synchronization works best when the master oscillator here is at a lower pitch and this one is at a higher pitch. And as I explained in the text of this month's column, what happens is that each time this guy starts a new cycle of its waveform, this guy has to start over too. You can see this abrupt break in the waveform there. That's because this one, which is the one we're going to listen to, has to synchronize. It has to start over at 0, the 0 being the line there, when it sees a rising edge coming from this oscillator over here. And as you can hear, the actual pitch of the fundamental is dictated from over here. It doesn't change. What changes is the synced waveform has to shape itself based on the fundamental coming from over here. Now, there's also a hard versus soft sync switch, and you will find that useful. Let's listen to the difference. I kind of like that. Now, to finish this out, what we're going to do is we're going to run the sound of a sawtooth. The raw oscillator is not necessarily all that nice by itself. So do we want sync on this? Well, maybe not. Let's get rid of this sync. Often we want to shape the sound coming from an analog oscillator by running it through a filter. And so that's what we're going to do here. We have a sawtooth wave here. Doesn't sound like a sawtooth though, because I'm running it through the filter. Let's put the sync back in. What the heck? So that's a good introduction, I hope, to the business of using an analog type oscillator. See you next month.